partition function. So if you remember in the last class, we did Maxwell-Boltzmann distribution, and we actually found out this equation. Okay, so this is the equation that we have found the other day, and then we are going to use this equation to understand something which we call as the partition function. Now we need to understand the fact that whenever we are talking about statistical mechanics, we are talking about more particles. Okay, we are talking about more of particles. So if there is more particles, more molecules involved, the answer or the result that we are going to get is will be or closer to the reality. Okay, so that's very important, and that's why we are using a large system. Okay, more molecules and all. So some of the terms I have not explained, and these things should be known to you from your basic idea of thermodynamics. Okay, so what is usually a partition function? So this is no doubt a function, just like you write down an equation in terms of x and y. This is also an equation, but then it has got certain specific meaning in statistical mechanics. Okay, so whenever I say partition function, and you know that statistical mechanics is a system which is more closely related to thermodynamics. That means temperature plays a very important role. So partition function is a function of temperature T, okay, usually denoted as T, and the microstate energy. Now if you remember, 2 weeks back we did study about microstate and macrostate, but then if I just give you a very brief understanding of this, we already know that if we have a close surrounding, and let's say we have divided into 3 regions. Okay, this is, let's say, 1, this is, let's say, 2, and this is 3. So if the system is given some temperature, let's say 100 Kelvin, okay, the chances are, and then definitely it happens, that's the classical idea, that all the particles will be in motion. So if all the particles are in motion, it means that there is no potential energy involved. There is only kinetic energy that we are talking about. That's the classical idea. Okay. Now, the chances are that all of them might not be having the same kinetic energy. It might be the same system, but then if we're applying a temperature, it's not that all of them will move with the same kinetic energy. That's also an important assumption to understand the system. So what we can say that a number of particle will move with energy E1, let's say N1 number of particle. A number of particle will move with energy E2, a number of particle will move with energy E3, and so on, depending on the system. Okay. So based on this, what we can say is that the particles are moving with energy E1, E2, E3, okay, within the system. And if we are dividing it, we say it has got by microstates. So in this particular case, we are talking about 3 microstates. But then, you know, if you are considering a practical system, many particles would be there with certain energy, some other particle with some other energy. So there will be a number of energy distribution, which is more or less continuous in nature. That is also something which we studied in classical mechanics. So if it is continuous in nature, it simply means that we are going to do some integration here. Okay. So before we proceed or jump ahead, let me just read this again. The partition function is a function of temperature T and the microstate energies E1, E2, E3, etc. Okay. So microstate is simple. We take a system and we divide it into different you can say different chambers having similar properties. Okay, each of these chamber has got similar property. Now this partition function is actually applicable in a number of things which you might have already studied, maybe in your chemistry or even in your physics. Okay, when you are studying your thermodynamics part. So what happens is this. Okay, what usually happens is this. So when we talk about the Helmholtz free energy, we have an equation which is written as A is equal to minus KBT into ln of Z. This term Z is basically nothing but your partition function. Okay, so this is actually the partition function. So this is important, first point. So I'm not saying that it's only used in Helmholtz energy, but this is applicable in practical thermodynamics. Secondly, if you consider internal energy, this equation also you might have come across, or in the future you'll derive in statistical mechanics class, or when you study detailed thermodynamics, minus del beta of ln z. Okay, So if you remember in the last class, we did use the term beta and alpha, and we called them as the Lagrange's multiplier. Okay, but in general, we can say that beta is equal to 1 divided by kt. Okay, it's based on Boltzmann constant. Okay, so basically it is derived. Okay, but then we are not studying it right now. We'll do it in the near future. So the internal energy is also this, and here also we have got partition function. The aim is not to derive Helmholtz free energy or internal energy. The aim is to understand partition function. So before we understand partition function, we have to look into the application. Okay, so it is used in Helmholtz free energy and internal energy, which is important. Okay, so we need to note, I think this I already explained, that E1, E2, E3 are the different energies of set of particles. Okay, sum over states is the partition function. So if we consider the sum over all these energy states, okay, so this is the second point, huh? This is the first point. If we consider the sum of all these energy states, okay, we basically get the partition function. So what we are going to do is we are going to derive partition function now. When we considered the Maxwell-Boltzmann distribution, so this will be a question. So if I ask you what is partition function, maybe you can explain up to this particular point and it will carry around 1 or 2 marks, okay? Not very complicated. You can write down the final equation also, which we will see now. So let's derive it. Okay. So we have Maxwell-Boltzmann distribution, and this is the equation that we derived in the last class. We of course written it in a different form. We have written Ni is equal to Gi e to the power minus of alpha plus beta epsilon I. Okay. So alpha and beta are constants. Okay. So even if you don't remember the term Lagrange's multiplier, you can still use the term constant. Okay. And then epsilon I is the energy of microstate. But here you see what we are doing is we are considering a single microstate. We are not considering n number of microstates. Okay, so when we are deriving, we are considering a chamber within the system which has got epsilon I energy. Okay, but then now what we are going to do is we are going to consider the entire set. So for that reason, what we say is that the total number is actually nothing but summation Ni. Okay, so the distribution would be summation Ni. So it will be n1 plus n2 plus n3 and so on. Okay, so what we do is we just added summation sign, so it's not very complicated, I guess. So it's like the total number, we'll just put summation Gi e to the power minus alpha e to the power minus beta epsilon I. We're just playing around with the exponential term. Okay, we just separated them out. Okay, we'll look into the application now. Now you know, if we are actually considering a summation, you see e to the power minus alpha is basically a constant. Okay, it doesn't have any I there. Okay, so it's a constant, no doubt. Okay, so we can just take it outside and write it as capital A, let's say. So capital A is nothing but e to the power minus alpha, which is nothing but a constant. Okay, so this is important. And what I do is I simply write it down as n divided by a. Okay, so this total number divided by this constant e to the power minus alpha is actually the partition function. So this is what this partition function is all about. Okay, and that is given by summation Gi e to the power minus beta epsilon I. Okay, now if we consider Gi as 1, okay, so if you study more of quantum mechanics, you will see that this Gi actually corresponds to something which we call as degeneracy. Okay, so you have got a single energy level. Okay, got a single energy level with a number of energy states there. Okay, so what happens is we have number of particles bearing the same energy in the energy level, and that is basically called degeneracy. So if you consider this degeneracy as 1, okay, in general, so we can take it as the number can be kept there. Okay, it doesn't change any result, but what we are doing is we are just simplifying things here. If we just consider this degeneracy to be just 1, I'd request you, all of you, to please check the meaning of degeneracy clearly. Okay, it's a longer explanation, but the idea is simple. Okay, so that might be an assignment for you, and maybe I can ask you the next class. Okay, so I hope you go through that. So this Gi is actually the degeneracy, and then the partition function is given by summation e to the power minus epsilon by kt. As I said, beta can be taken as 1 divided by kt. I think 1 divided by kt is also a system of unit that is actually considered in many cases. Okay, so K is nothing but the Boltzmann constant and T is the absolute temperature. Okay, so this is what we do. So this is called partition function. So if I ask you for derivation, this is a very short derivation. If we have done Maxwell Boltzmann distribution, we are going in sequence. So if I ask you for what is partition function, maybe you can define these things, okay, and then you can just write down the final form that I have shown, and then that might be a 2 marks question, okay. And in the next part, if I ask you derive partition function, then you can just simply write down the equation. See, this is a general equation, okay. This is a general equation. It depends from system to system. In the next section, we are going to derive the partition function of an ideal gas. So we're going to use it, okay. So if I ask you to derive this, might be this, I'll give you around 3 marks, okay. So maybe this will constitute a 2 plus 3, 5 marks question, or by part 2 or by part 3, okay. So this is what is partition function is all about, and this is how you derive it from Maxwell-Boltzmann distribution. So it's all connected. I'm trying to be as sequential as possible, okay. So since we had a glitch at this beginning, so we are obviously not going to take any break. We're just going to finish this topic, okay. Don't worry, it's not a very long class for today. So what we are going to do now is we are going to find out the partition function of a gas molecule, okay. So let me tell you this a simple idea that when we are considering gas molecule, okay, you have a system which are having a number of gas molecules within it, okay, and all these gas molecules will actually possess only kinetic energy, as I explained, okay. So that means whenever I say total energy or the mechanical energy of the gas molecule, we are only talking about the sum of kinetic energy of individual molecules. So if you look into the classical picture, the things become slightly simpler, because you see, if I talk about the potential energy also, the things will become more and more complicated. So it's not that we want to make things easy. The thing is that the chances of having kinetic energy is maximum compared to a gas being stationary whenever we are applying some kind of temperature, okay. We are not making things easy. This is also a practical understanding, okay. So we have the sum of kinetic energy of the individual molecule. So it will become a lot simpler now, okay. And now what we are going to do is we are going to relate it with classical mechanics. So you see, what we are going to find out now is what is the number of energy level in the momentum range P and P plus dP. Number of energy level. Where do we use this energy level? This is your energy that we are talking about, okay. So we are going to use it, but then the number of energy level in the momentum range P and P plus dP. Now understand this. You have a chamber and then you have got a gas molecule. It will definitely follow different paths. It will go, it might be another gas molecule, follow this, and then it will go somewhere here. So it will actually have a path to move around, okay. That means that if we want to have an information of the path also, we should also consider momentum. From where did we learn this? We have learned this from classical mechanics when we were studying Hamiltonian. In the Hamiltonian, we did had the generalized momentum. So when we have generalized coordinate and information on generalized momentum, we can actually find out more information about the path of motion, okay. And whenever we have got momentum and coordinate involved, we no more call it as configuration space, we call it as phase space. We call it as phase space, okay. So this is very important. So we'll do just one assumption here, a very simple assumption, that gi, okay. So you can see here we do have gi, okay. Here this case we took just one, okay, but let's take this case of gi now. Gi is number of cells in a group, okay. So let's say you have got a box, okay, and you are dividing it into groups, okay, and within this group, okay, how many cells are there, okay. So these are the groups, okay, these are the groups here, these are the groups, and within these groups how many cells are there, okay. And how exactly do you find that out? Okay, so this is actually a simple maths. You have to know what is the volume of the phase space. So you have to find out what is the volume of that particular cell in the group, okay, divided by volume of one cell. Okay, understand this. If you have the total volume, okay, and if you have, let's say, these are the, let's say, cells, okay, these are the cells, and all of these cells has got equal volume, okay. Obviously my diagram is not good. All of them are, let's say, equal, okay. So if I can find out what is the total volume here, total volume, okay, and then divide it by the volume of each cell, I can know how many number of cells are there, okay, because these cells are divided equally, okay. So let's say I'll take this example. I can make it more simpler here, I guess. If I consider these three, let's say there are three cells here, okay. How do I know? I can simply take the volume, okay, and then I can divide it the volume of each cell, okay. So that will actually give me how many numbers are there. So I'll find out that this is eventually 3. You can take a value and do it. I think it's all simple, okay. So if the, let's say, if the volume of one total volume of the phase space is 9 and each cell has got a volume of 3, I know that the total number of cell is 3. So we are using this logic here, okay. So this is a very simple maths. Try to understand it, okay. Now how do I find it out? Now you see, we are talking about phase space, okay, and we are talking about a continuous nature. It is not discontinuous. So if you are adding, let's say, 1 plus 2, okay, plus 3 and so on, what you do is nothing but summation. This is something which you already know, okay. But when you are adding between 1 and 3, all everything, not a single point should be missed out, okay. That is actually considered by using integration. So that's a very important concept that we learn from maths. Now here we are considering that there is a large volume, okay, of cells. Number of cells are much more. So we don't consider it as a summation of 1 plus 2 plus 3. We consider it continuous, and as a result we take integration and not summation, okay. So when we talk about integration, we do have x, y, and z, okay, and then we have got the momentum px, py, and pz, okay. So when we consider these 6 coordinates, okay, because we do consider it as the position coordinate and also the momentum coordinate, we have to take 6 integration signs. So that's why there are 6. See, 1, 2, 3, 4, 5, 6 divided by volume of each cell, okay. So we do consider that the x, y, and z direction of each cell is nothing but h, okay. So it will be h cubed, okay. And then when we consider in the configuration space dx dz, that means we are considering the volume of the entire box, okay. So we are considering a 3-dimensional box, and let's say the length along the x-axis is x, along the y-axis is y, along the z-axis is z, and so on, okay. So my 3D diagram has been horrible here, but anyway, you understand the fact here that this is x, y, and z. So if I want to find out the volume, that would be integration of dx, dy, dz. And when I take that, 3 of the integrations I have taken care of with dx, dy, dz, and that will give me the volume here. So I have considered the volume in the configuration space, but then there is also momentum. So I have to calculate this part now. Happens to calculation of the momentum phase space, okay. This is one of the easier parts of statistical mechanics, not much complicated if you understand basic maths here, okay. So let's try to find out what is the volume that is being occupied by the momentum coordinates, okay, so that we can understand what is the path that it will follow. So let's consider momentum coordinates, okay. So you have to refer back to classical mechanics to understand what are momentum coordinates that we're talking about. But I think this is simple. What we do is, for now, we do say that, let's say we have got a coordinate system. This is the, let's say, the y part. Let's say this is the x part of the momentum, and this is the z part of the momentum, okay. And as the diagram shows, maybe all of them are equal, okay. Let's say all of them are equal, okay. And then what I do is I basically, because you see, if you are considering a single system, the chances are that the momentum along the x, y, and z direction might be the same. Okay, so we basically consider a sphere. This is three-dimensional, not two-dimensional, because we are considering a reality here. Okay, might move along the x-axis, along the y-axis, or along the z-axis. So let's say from here to here, this that means that's the radius, right? Because this is the center. So this from here to here it's p. Okay, and then you see we need know p, we need to find out what is dp. What is dp? So that means we can actually draw another circle outside it. Okay, outside this, and this length would be nothing but dp. Okay, so that means if we consider this entire length, this is p plus dp. Okay, now you want to find out this part. That is what is that integration is all about. Okay, you want to find out what is the volume of this part. Okay, this is very simple. So how do we find it out? This is okay. So you see, we're finding out this volume. Okay, so if you want to find it out, you can simply say that I can take the entire volume here. Okay, so this is the physical meaning of the integration that we are doing. Okay, what is the entire volume of dp dx, dpy, dpz. Okay, so if I consider and try to understand it, okay, it will take some time, but then if you think about it, you will think that this is correct. Okay, so if we consider this entire volume, so let's consider this entire volume now and try to find out what is the volume. So you know, volume of a sphere, okay, is 4 by 3 pi r cube. So 4 by 3 is there, pi is there, same. But r, what is our radius for this entire sphere is p plus dp. So this will be p plus dp cubed. Okay, pi r cubed minus 4 by 3 pi p cubed. So we are going to subtract this part. Okay, this part. So I think I can just do this dot dot dot, and we are going to subtract this part. So if we take the entire volume and we subtract this center part, we are going to get this part. So if you just do the maths, 4 by 3 pi can be taken out. Okay, and within the bracket we have got p plus dp cubed minus p cubed. Okay, so what happens here is we can just expand it 4 by 3 pi, and then this is p cubed plus dp cubed plus 3p dp into p plus dp, right? A plus b whole cubed is a cube plus b cube plus 3ab into a plus b, that formula, minus p cubed. So you can cancel out this p cubed and this p cubed. Okay, you are left out with this term dp cubed. Now this dp cubed can be ignored. Okay, this can almost be considered as zero. What is the reason for that is dp is actually considered to be a very small variation. Okay, so if it is a very small variation, we can actually take the cube of this, and cube will be even smaller, so we can ignore it. Okay, similarly, if you multiply 3 dp dp with dp, the second term would be nothing but 3p square dp. This can again be ignored. Okay, so we can ignore this term because of p square, we can ignore this term because of dp cubed. Okay, this is dp square, this is dp cubed, we can ignore both this term, and we have got is 3p square dp. This part, just 3p dp multiplied with p, so you get 3p square dp. Okay, that's important. So if you do this, what we get is a simple answer. The simple answer is 4 by 3 pi, 3p square dp, 3 gets cancelled, and we simply get 4 pi p square dp. What did we get now? Because we did so much sum, we got the momentum part. Okay, and what we are aiming to find out is the number of cells in a group. So if I consider gi, I have this part and this part, and I will replace this now. Okay, so if I replace it, let's see what do I get it. Okay, so the final answer that I get is v 4 pi square dp h cubed. Okay, now don't get confused here. Okay, we are actually finding out within this small region, okay, the number within this small momentum region dp. Okay, now see, you might question me that, sir, you said that when I take dx, dy, dz, I consider the entire volume, right? But when I take dpx, dpy, and dpz, I'm not considering the entire dp plus p plus dp. Why don't I consider only this part? Why should I consider this part? Why I am going to subtract it? Okay, because the aim is here to find out the number of cells in a group within this space of dp. Okay, within this space of dp. So we are finding out the variation in a small momentum space. We are going to find out the small variation in the small momentum space, and that's why we are taking it dp, not x. Okay, within that x, what is that small dp? That is what we are finding it out. Okay, and that's why I have taken dpx, dpy, dpz as this entire volume minus this volume. Okay, so please try to understand this, very important. Okay, so we have got gpdp is equal to this, but is our work complete? No, not yet, because if you remember the equation, we have to find out what is the energy. Okay, we are going to use it, but first we are going to find out what is the energy. So we have to find out what is the energy form epsilon. Okay, which is actually power of e, power of exponential, very important. Okay, so let's see we can find it out or not. What we do is simple. Momentum is equal to mass into velocity. Momentum squared is mass square into velocity square, which can be written as momentum into mv square. Okay, so if we take momentum into mv square, it is simply mv into half mv square. Okay, we can do that maths, very simple. I think with these things we have done again and again, so we can simply write it down. P square is root 2 me. Okay, if we write down p square is 2 me, that means p is root over 2 me. But then here, in this particular case, we are interested in finding out what is dp and not p. So if we just want to find out what is dp, we simply find out what is dp from this particular equation. So I don't need to show you the math, although it's already there on screen, you can see. If you do dp, you will get 1 by root 2 me into m d epsilon. Okay, how this is also, okay, this is also e. I'm calling it as e only, because I'll just take it as e. You can write it as epsilon, I think it's fine. So how do I find out this dp? Simple, you just differentiate d p with respect to epsilon. So dp d epsilon is equal to d epsilon of root 2 me. Okay, that is what is there. And then you do your normal differentiation. Sorry, just take this root over 2m outside, and then there is epsilon to the power half, so it is nx to the power n minus 1. So half epsilon to the power half minus 1, it will be root over 2m divided by 2 root epsilon. Okay, then we just rationalize age old thing, right? Plus 8 9, then it's simply m divided by root 2 me. So that's why it is m divided by root 2 me. And then this d epsilon will come here, right? So that's why this is dp is this. Okay, so I think this is simple math. In exam, don't show this. Okay, I expect that you know it. Okay, but I'm showing it because I prefer to be very much detailed. Okay, so that we have all our answers clear. Okay, so what I did was I had the form in the form of momentum, and now I changed everything in terms of energy. So to change in terms of energy, I should know what is dp, which I've just now found out. I should know what is p, which we also have found out. So, okay, so just what we are going to do is we are going to replace. So that means this will be now g epsilon d epsilon. Okay, I'm going a bit fast because I think this is very simple. Okay, and anyway I'll put the recording. You can always pause and watch it. Okay. So this is g epsilon d epsilon. V was already there, 4 pi was already there, and then h cube was already there. P square we found out to be 2 me, so this one we have replaced, and dp we have found out to be m d epsilon by root 2 me. So this one we have also replaced. Okay, let's do a bit of algebra here, do a bit of correct changes. Okay, so what we do, v into 2 pi divided by h cube. Mind you, please don't start cancelling or combining 2m epsilon by root 2m epsilon in exam also, because it has got some importance. I'll tell you what. Okay, so you see you have got a 2 here, you put the 2 here and take this 4 on this side. So if you take 4 on this side, this will be 2 square, so this is 2 square, and then you have got this m and this m, so this will be 2m square. So it will be 2m square divided by 2m to the power half, so this is 2m to the power half. I've only taken this part, and I have taken epsilon separately. Epsilon divided by epsilon to the power half into d epsilon. Okay, so v into 2 pi 2m, this will be nothing but 3 by 2 into epsilon to the power half, because that's 1 minus half, into d epsilon divided by h cube. Okay, still not complete, some more on there. Okay, so this is the form that we have of g epsilon d epsilon. Okay, so when I said partition function, you will ask me, sir, why have you taken gi as 1? Because we just considered it to be the simplest form of the partition function. Okay, but then if you consider a real case, you cannot ignore gi, because gi is degeneracy, so we are considering gi here. Okay, and if we consider gi, we have to find it in terms of g epsilon, because you see there is an epsilon here also. So we are going to write down this gi in terms of epsilon. So this is G epsilon D epsilon. Okay, we're just going to replace it. So what we are going to do is we are going to replace this Gi now. Okay, in terms of epsilon. So whatever we had here. Okay, maybe I can just zoom out a bit. Okay. Mm, okay, we have it both on the same screen. Yeah. So you see, this is your G epsilon D epsilon or Gi. So I'm just going to replace it here. V 2 pi 2m3 by 2 epsilon to the power half d epsilon divided by h cube, and then e to the power minus epsilon by kt. Okay. Now you might ask me that why are we taking an integration sign in place of a summation sign? Okay, because in classical mechanics or in classical approach, what we do is that the distribution of the energy state is considered continuous. The distribution of the energy state is considered continuous. Okay, I hope you already know it. Even if you don't know it, at the beginning of the class I told you what is the difference between summation and integration. Okay, so then if we just replace this with summation here with integration, we have this, and this is replaced by integration. Okay, and now you see this is actually a integration. Okay, we have to do an integration with respect to d epsilon. Okay, so what we do is we combine the epsilons together and try to integrate them. So let's just do it. Okay, so whatever is constant is taken out. V into 2 pi into 2m to the power 3 by 2 divided by h cubed taken out. Inside we have got epsilon to the power half into e to the power minus epsilon divided by kt into d epsilon. Now this is where I won't like to help you right now, because this is something which you might be doing in your mathematical physics. Okay, so what happens in mathematical physics is you get certain complicated integration term which you integrate. Okay, so if you integrate this particular term, this actually can be done using the concept of Gaussian integral. Okay, so even if you have not done it, you may be doing it in the near future. Even if you have done it, then you already know it. Okay, and you know this particular term actually depends on what is the power of epsilon here. If the power is half, this is the answer. Okay, if the power is something different, in general it's written as n, this will be different. Okay, but then the power is half, so I've just the answer, and then this is something which you have to remember here, because if you do this also, this derivation is going to be very long. Probably it will take more time, and uh, doing justice to the mark will be a bit difficult. Okay, for your exam purpose. So if you just remember this, this is root over pi divided by 2 into kt to the power 3 by 2. Okay, that's the answer to this integration. You have to remember this. That's from Gaussian integral. And then that we can say is z is equal to v into 2 pi 2 and 3 by 2 divided by h cube, and this term. So what we do is we cancel 2. You see there is a pi, there is a root over pi. That means pi into root pi will give you pi to the power 3 by 2. And here also we have got kt to the power 3 by 2. We can just put it inside the bracket, and then we can combine everything together. Now we can combine it. Okay, it is 2 pi mkt whole thing to the power 3 by 2. V is dot 2 pi mkt 3 by 2 divided by h cube. This is the partition function of the gas molecule. Okay, of a system of gas molecules. So what does it actually tell us? It gives me an information about the energy distribution. See, the total energy of the gas molecule is practically equal to the sum of the individual kinetic energy. So that means if I basically consider a simple equation of a simple partition function, let's say summation e to the power minus epsilon divided by kt, I can say that, let's say this I. Okay, this is I. That means it goes from, let's say I is equal to 1, 2, 3. There are 3 values. So it will be e to the power minus epsilon 1 by kt plus e to the power minus epsilon 2 by kt plus e to the power minus epsilon 3 by kt. That means it gives me the information about the energy distribution within the gas molecule at a particular temperature. Okay, at a particular absolute temperature. And this is what the final equation is all about. See, the final equation does have temperature which can vary, and based on that you will be having different partition function. And it is quite logical that if the system is big enough, the volume is more, the partition function is going to vary, because there will be more distribution of energy. Okay, so that's why this partition function is very important. It gives me a very clear idea about classical ideal gas.